Hello, statistics students. This is Jami, and this video is starting our chapter 6 through 8 presentation. Chapter 6 is on normal probability distributions, and section 6.1 is on the standard normal distribution. Let's discuss uniform distribution first. Uniform distribution is data that takes on the shape of a rectangle. Here's a good example for you. All of the continuous random variables are evenly spread among the range of probabilities. So if this were a dot plot and you started plotting all these voltage levels, well, we know in a dot plot when you have repeated data values, you have to go up vertically. So if you were to continue plotting all your data values, you would find, and if you found that it takes on the shape of a rectangle like this, then you have data that is uniformly distributed. All right, so this topic is how we can use area to find probability. So uniform distribution is perfect to start this topic out because we know the formula for the area of a rectangle, and it is base times altitude. Okay, so let's look at this example. Find the probability that a randomly selected voltage level is greater than 124.5 volts. All right, we know that all the data is contained in this rectangle. So had they asked us the probability of randomly selecting a voltage level and it being in this large rectangle, our answer would be 1 because it is certain to occur. But they're not asking us for the whole thing. They're asking us about 124.5 or greater. So we can find that area by doing base, which is 0.5, times height, which is 0.5, giving us an area of 0.25. This is also a great example because we can divide it into 4 equal parts, and we can see that the area shaded is 1/4 of the total area, and therefore the probability would be 1/4 or 0.25. If you understood that, then you should be able to answer this question. I'm going to make a slight adjustment to the question. I'm going to change it to less than 124 volts. Please pause the video and try that now. Welcome back, and here is my solution. 124 is where we put the vertical line. The less than inequality tells us to shade to the left, and we can see that that is half of the total area. So the probability that a randomly selected voltage level is less than 124 volts equals 1/2 or 0.5. Standard normal distribution, on the other hand, takes on the shape of a bell-shaped curve like this. So if we were asked to find the area or the probability that a randomly selected data value is greater than 2, for example, here's our vertical line, and our shading would go like this. But that's not a rectangle. That shape, we don't have a formula for the area of that shape. We could use calculus and limits to figure it out. But instead of deriving that from scratch, we're going to use the calculus that other people have already developed for us, and we're just going to run a program called normal CDF. Okay, you're going to run normal CDF if you are given a z-score, or maybe 2 z-scores that it says find the probability between the two, and then you are asked to respond with the probability. So you'll find the area, and that will be the same as the probability. Normal CDF requires 4 inputs. Lower z-score, which in this example would be the 2 because that is where the shading starts. Upper z-score, which in this example would be tempting to go 3, but it's not. It's not 4, it's not 5. We don't know what it is. That curve approaches that horizontal axis, but it doesn't touch it. So for our upper z-score, we're going to have to use some random high number, like 999. Third input will be your mean, mu. And if you're dealing with z-scores or standard normal distribution, mu will always be 0. Fourth input, sigma. And again, if you're dealing with z-scores, so standard normal distribution, your standard deviation will always be 1. Okay, let's take the opposite situation, or in math we call it the inverse operation. Here, we're given the area and we're asked to find the z-score. In that case, we're going to run the program called inverse norm. Inverse norm requires 3 inputs. The area to the left, in this example, would be the 0.95. Contrary to the area of the right, just want to point that out right now, that the area to the right would be the 1 minus 0.95, which would be the 0.05. That is the area to the right of this particular z-score. Mu, which would be 0 if we're talking z-scores, and sigma, which would be 1 if we're talking standard normal distribution z-scores. Let's try some examples. Bone mineral density measures are normally distributed. When you read that normally distributed, I want you to visualize a bell-shaped curve. A bone mineral density test can be helpful in identifying osteoporosis. The results are measured as z-scores. Z-scores, when you see that, I want you to start to think, okay, mu equals 0 and sigma equals 1. They want us to find the probability that the result lies between 0.7 and 1.98. I'm just going to sketch a little graph. I'm going to put the letter Z next to it. 0 goes in the middle. 1, 2, 3, 1, 2, 3, just so I can visualize the empirical rule. Okay, now I'm going to switch to blue. And the 0.7 would be maybe right about here. And the 1.98 would be really close to 2, right there. And the shading is always determined by the wording. This one says between, so we shade between. Okay, so we're ready to run our program. We are given 2 z-scores and asked to find the probability, which means we need to run normal CDF. Our lower z-score will be 0.7, our upper will be 1.98. Mu is 0, sigma is 1, and if we run that correctly, we'll get 0.2181. Now they want us to find the result, find the probability that the result is a reading less than 100, 1.27. Let me switch to purple for this. 1.27 would be right about here, 1.27. And the shading is dependent on the words. We've got the less than inequality here, so we would shade this way of the 1.27. So part B is only addressing what I'm doing in purple here. Okay, so we're given a z-score and we're asked to tell them the probability. That means we need to run the program normal CDF. The lower z-score is where your shading starts. This can be a little tricky, which is why the visual is so helpful. Where does the shading start? Well, this is standard deviation of -1, -2, -3, or 3 standard deviations below the mean. So the shading doesn't necessarily start right there. We don't know where it starts exactly. So we're going to use some random small number like -9,999. Our upper z-score is where the shading stops, 1.27. Mu is 0, sigma is 1, and if we run that correctly, we should get 0.8980. I'm going to keep that graph for one more example. Find the probability that a randomly selected result is above -1. Let me switch to black for this. Okay, -1 is the z-score. Put a vertical line right there. Shading depends on the wording. It says above, so I'm going to shade this direction. Ignore the purple and the blue. Part C is only for the shading in black. Okay, we're given a z-score and we're asked to tell them the probability. So we need to use the program normal CDF. The shading obviously starts at -1. The shading not so obviously stops at some random large number. So I will use positive 9999. Mu is 0, sigma is 1, and if we run that correctly, we get 0.8413. I'm going to erase the graphs now. Part D wants us to find the z-score that separates the lowest 15% of results. Okay, this is where things are changing on us. Now they are providing us with the z-score, and they're requesting the z-score from us, and they've given us the area, the lowest 15%. The lowest 15% would be over here as an area that would be 0.15, and this is the z-score that we are trying to find. So we don't run normal CDF, but rather we run inverse norm. Inverse norm requires 3 inputs. It'd be the area to the left, which is 0.15. Mu is 0, sigma is 1, and if we run that correctly, it turns out that the z-score negative 1.04 will be the dividing z-score of the bottom 15%. All right, last example. I'm going to erase that graph. Well, I'm going to leave that graph a little longer. Find the z-score that separates the highest 15% of results. So that would represent an area like this, 0.15, and this is the z-score we're interested in now. It's going to be a positive number because mu is 0. Okay, we're going to run inverse norm. Inverse norm's first input has to be the area to the left of that z-score. The area to the left of that z-score is 1. That doesn't look nice. The area to the left of that z-score is 1 minus 0.15, which is 0.85. Mu is 0, sigma is 1. So if we run that with inverse norm, turns out that a z-score of positive 1.04 will separate the top 15%. Not a coincidence that we got negative 1.04 and positive 1.04 because the bell-shaped curve is symmetric. And what I mean by that is if you were to cut this little graph out and fold it along this dotted line, the negative 1.04 and the positive 1.04 would match up. 6.2 is on real applications of normal distributions. Everything in 6.1 was talking about z-scores. Standard normal distribution is when we're talking z-scores. So it was nice. Mu was always 0, sigma was always 1. But if we're given a set of data and it is normally distributed, but we're not talking z-scores, therefore it's not standard normal distribution, then we call it non-standard normal distribution. Sigma will not necessarily be 1, mu will not necessarily be 0, and we're not going to be talking about z for z-scores. We're going to be talking about the random variable x in whichever value we are given it. Mu will still go in the middle, that'll be nice. The probability under the curve, under the entire curve, will still be the area of 1. So when we run normal CDF this time, we'll give the lower x value, the upper x value, whatever mu happens to be, and whatever sigma happens to be. Tall Clubs International has a height requirement that women must be at least 70 inches tall to join. Women have normally distributed heights. When you see that, I want you to start thinking of a bell-shaped curve. With a mean of 63.8 inches, that's going to be our mu, and a standard deviation of 2.6 inches. That's going to be our sigma. and they want us to find the percentage of women who satisfy the height requirement. So we're not going to put a Z, we're going to put an X because we don't have Z-scores here. We're not going to put a 0 in the middle, we're going to put a 63.8. And our standard deviations will be traveling out plus 2.6 inches, plus 2.6 inches, plus 2.6 inches. And in the other direction, minus 2.6 inches, minus 2.6 inches, and minus 2.6 inches. Okay, where are we going to make our vertical cut and what side are we going to shade? That's the next thing we need to figure out here. It says that you have to be at least 70 inches tall. So our vertical cut is going to be at 70, and we're going to shade to the at least 70. I'll talk to you about that in just a second. I want to find where the 70 is at on the x-axis first. 63.8 plus a standard deviation of 2.6 puts me at 66.4. I'm going to travel up another standard deviation of 2.6. That puts me at a woman's height of 69 inches. And one more time, traveling up a standard deviation of 2.6. That puts me at 71.6 inches tall. So, not that it was necessary to be to scale like that, but it helps me feel more comfortable in drawing this vertical line at some 70 inches, some approximate 70 inches. Now it says at least 70. That's tricky. At least 70 would mean greater than 70 inches. So I'm going to shade this direction. Okay, now that I've got a visual, I think I can do this. I run normal CDF. The shading starts at 70. The shading stops at some random large number. I'm going to make an adjustment for mu, an adjustment for sigma, run the program. 70, 9,999, mu is 63.8, sigma is 2.8, and if I run that correctly, I get 0.008548483, and so on. Now answering the question, which is, find the percentage of women who satisfy the height requirement, means I need to change this into a percent, and then they want me to round to the nearest hundredth. So please be careful when you're rounding percentages. Make sure you change it to a percent first. 5, 4, 8, 4. Did I even do that wrong? 5, 8, 4, 8, 4, 8, 2, 3, dot, dot, dot. Whoops. And then switch it to a percentage by moving the decimal twice. 1, 2. Oh my gosh, I already did that. I screwed myself up when that screen got zoomed in. Let's do this again. Okay, first things first, change it to a percent by moving the decimal 2 places. So now we have 0.8548482 dot 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 percent. Now do your rounding, and that would take you to 2 decimal places because it says nearest hundredth, so it'd be 0.85%. And it turns out that less than 1% of women will meet that height requirement to join that particular club. When designing aircraft cabins, what ceiling height will allow 95% of men to stand without bumping their heads? Men's heights are normally distributed with a mean of 69.5 inches and a standard deviation of 2.4 inches, rounded 2 decimal places. I know that can be overwhelming when you read that question in its entirety, so break it down for yourself. First things first, when you see normal distribution, I want you to draw a bell-shaped curve. It doesn't have to be perfect. Just don't pull out a ruler. Just sketch a horizontal line and a bell-shaped curve over top. Next, decide if you're going to label the horizontal axis with the letter X or Z. It doesn't say standard normal. It doesn't say anything about mu being 0 and sigma being 1. So this is the x-axis. Mean goes in the middle, 69.5 inches. And then your standard deviation of sigma is 2.4. Okay, so that would go out up 2.4 plus another 2.4 plus another 2.4, minus 2.4 and minus 2.4 and minus 2.4. Not going to label those or calculate those quite yet. I may not need them at all. First, I'm going to check and see what they're... Okay, they want 95% of men to be able to stand without bumping their heads. So I'm going to start shading in the area of 95%. All right, I want to start on this side because I know these guys will be able to stand the easiest because they're the shorter men. These guys will be able to stand. If I wanted half of the men to be able to stand without bumping their heads, I would stop at a ceiling height of 69.5. But we want more than half. We want 95% of men to be able to stand. So I'm attempting to shade in 95% of this curve, which I'm not quite sure, where to stop. So what I'm going to do is run that program called inverse norm, and it's going to tell me where to stop, making sure I have obtained 95% of the data, or 0.95 of the area. Okay, first input needs to be area to the left, which is 0.95. Mu needs to be 69.5, and sigma needs to be 2.4. It'll look like that when you input all of it, and if we ran that correctly, we'll get 73.4476487 and so on. So accurate to 2 decimal places, we would need ceiling heights of 73.45 inches to allow for 95% of men to stand in a certain aircraft without bumping their heads. Here are 2 examples for you to try. Please pause this video and try these on your own, and then return when you're done. Welcome back. Here are my solutions. This population mean is 15.2, so that goes in the middle. Standard deviation is 0.9, so that is my sigma. And they want us to find the z-score that separates the, typo, the top 20% of the population. Well, if you didn't pick up on that typo, you might want to pause this video again and finish trying this question. And top 20%, it's going to be, this would be half. So I know I want to be less than that. So maybe like right here. I'm going to label that 20. And this z-score, that x value right there is what we're trying to find. So we'll run the program inverse norm. Area to the left, if you typed in 0.20, you made the most common mistake, totally understandable. Take this moment to make sure you don't make that mistake again by recalling that first input has to be the area to the left of the x value you're interested in, which would be this area here, which would be 0.80 or 80%, if it's easier for you to think of it that way. Mu is 15.2, sigma is 0.9, giving us 15.96. This question here, we have a mean of 650, x values, standard deviation of $70, probability that a randomly selected teacher earns less than $550 a week. That's an x value. So they're telling us make that vertical cut at $550. Less than that would be here. And so this area is what we are trying to find. So we're not going to run inverse norm. We're going to run normal CDF. Area to the left, where the shading starts. some random small number where the shading stops, 550. Mu is 650, sigma is 70. I want to point out right now to be really careful when you type in that negative 999. I mean, if you used $0, you'd be fine, but if you're being consistent with me and using negative 9999, make sure you don't enter it with minus 9999. You need to enter it on your TI with the negative sign, and the negative sign is right below the 3. Okay, running that will give us 0.7066. And that will finish our discussion on section 6.1 and 6.2. Next video will be our discussion on 6.3 and 6.4. See you then.